Today we are going to talk about Kirchoff's rules. These are rules that use current and voltage to help you understand circuits and help you solve circuits and help you know what's going on inside a circuit. So there are two of Kirchoff's rules, and using the water analogy and the height analogy that I keep going back to, both of Kirchoff's rules make perfect sense. So that's what we will do. Okay, so the first of Kirchoff's rules that we're going to talk about is the current rule, sometimes called the junction rule. Okay, and the junction rule, or the current rule, says that the currents entering a junction. A junction is where two or more wires come together, and the currents leaving a junction, leaving that junction, have to be the same. They have to be equal. That's sometimes written in mathematical language, mathematical shorthand, as big sigma, sum of I currents, and then equals 0, and then just to remind us, we can put at a junction. So what that means is if I have a circuit, and let's say I've got a wire that splits into two pieces, and so I've got current that comes in here, and some of it goes, so let's call that I1, and then I've got current that goes here, that's I2, and current that goes here, I3. So the junction is right there, and it would say, well, okay, if I count incoming current as positive and outgoing current, that line, outgoing current as negative, then that would tell me that, okay, I1 minus I2 minus I3 equals 0. So think about that with the water analogy, saying, okay, well, electrical currents is like water current. So if you've got a fork in the river where the main branch of the river splits into two branches, then all we're saying is the amount of water that leaves in the two branches has to be the same as the amount of water that comes in the main branch. And when you say it like that, you just say, yeah, well, duh. It's not like, water disappears at at the fork in the river, or, water doesn't appear out of nowhere at the fork in the river. The fork in the river, if you add the two forks together, you get the same amount as you got in the main branch. That's all this law is saying. I suppose if you're thinking of it in terms of a river and water in a river, you would say, well, the net amount of water is conserved. You don't have more water entering than you do leaving. So you can think it, if you're thinking in terms of electrical current, you can say, well, this is the result of the conservation of charge, not of water, but of charge. So this is always true. We have never observed a case where the law of conservation of charge is violated in nature. So because Kirchoff's junction rule, or Kirchoff's loop rule, Kirchoff's current rule is a consequence of the conservation of charge, we've never seen violation of that in nature either. We can use that. Let me work on an example for you of when we might use this. Let's say we have a 10-volt power supply or battery, and I'm going to put two resistors in parallel with each other, and we'll say 5 ohms, and this one is 10 ohms. And if I wanted to figure out the total current, so we'll call that IT, the total current, then I could just figure out, well, what's the equivalent resistance of those two? So the equivalent resistance of those two, REQ, is equal to 1 over 1/10 plus 1/5, or 1 over, let's see, a tenth is, or a fifth is 2/10, so that's 1/10 plus 2/10, that's 3/10. 1 over 3/10 is 10 over 3, or 3.3, repeating, ohms is the equivalent resistance. So that means that I total, since V equals IR, that's Ohm's law, V equals IR, so I've got 10 volts, and it's equal to I total times the equivalent resistance, so that's 3.3 ohms. I total is 10 divided by 3.3, and I guess that's
3 amps. So what we have is that the total current of 3 amps minus I5 minus I10 is equal to 0. Well, how much current is going through each resistor? Well, we might notice that the 5 ohm resistor is only half as much as the 10 ohm, and since resistors resist current, that the 5 ohm would get twice as much current as the 10 ohm, and then you would say, well, if I need to break it up into thirds and one gets twice as much as the other, then the 5 ohm gets 2 amps and the 10 ohm gets 1 amp. That would be correct. But probably you wouldn't have thought of that, and even if you did think of it in this situation, it's quite likely that the numbers wouldn't be so nice. The next time we need a better way to figure out how much current goes through each resistor, so we can do that. To do it, we will need to use Kirchoff's other rule, Kirchoff's loop rule, or Kirchoff's voltage rule.
So I'm going to scroll up. Kirchoff's other rule, loop rule, sum of the voltage changes around any closed loop in the circuit is 0. And if we write that in mathematical shorthand, we would say, okay, well, sum of, that's capital sigma, and then voltages, that's V, and then to remind ourselves that it's around a loop, sometimes we write that there, equal to 0. Okay, so let me talk a minute about what does this mean physically before we use it in the example. Okay, what does that mean? Well, go back to the height analogy. Remember, voltage is sort of like height. So in the height example, sum of the voltage changes around any closed loop equals 0 means sum of the height changes around any closed loop is 0. So what that would mean is, let's say, okay, let's pretend we're back in Lapham, and I'm on the second floor classroom. And you're all sitting there in the classroom with me, and I leave. I go on a walk. Then I come back. I say, well, while I was gone, I might have gone upstairs to the third floor or the fourth floor or even the roof. I might have gone downstairs to the first floor or even down into the basement, or maybe I went outside and went up into Alumni Tower, and then I came back, and now I'm back here in the room with you. I have made a closed loop because I ended where I started. What's the total change in my height on my trip? Let's say 0, because you're standing right there where you were when you left. Maybe you went up. Okay, so that's what this says in terms of voltage. It says that if you start somewhere and you go around in your circuit and you end up back where you started, your total change in voltage is 0. It means exactly the same thing it would mean in the case of height. Okay, so what we do is, all right, I want to, let's see, let's call this, I'm still going to call this I10. I'm still going to call this current right here I5. Nope, it's kind of small for the I5. I want to find I5 and I10. All right, we already have the equation from the junction rule. We got that I total is equal to I5 plus I10. That's the one I put a big rectangle around. Okay, and I said that as long as you got that, you were good. Okay, so let's keep that. Now let's use the loop rule to get another equation. So to use the loop rule, you pick a spot in your circuit. Usually you pick next to one of the batteries or the power supply or whatever, but it doesn't matter. You can start wherever you want. But just kind of out of habit, I usually start at the battery. So I'm going to start right here on the negative terminal of the battery. Remember, the short end is negative and the long end is positive of the battery. Okay, so I'm going to start right there where I put that dot below the negative terminal of the battery. So now we have to go on our walk. We're going to go on a walk, and we're going to go around the loop until we get back to where we started on our walk. So you go, and then every time you have a voltage change, you write it down on the left side of the equation. So here's sum of voltages equals 0. So on the left side, I got to keep track of all my voltage changes. And then on the right, I'll have 0 when I get back to where I started on my walk. So, all right, and I'm going to go clockwise. So we're going to start here, and then we go up across the battery. Okay, so think of the battery. I mean, battery is like an up staircase, or it's like an escalator, I suppose. Okay, so that we went from the negative to the positive, so we're going up the escalator. And that means we have plus 10. Not plus 0, plus 10 volts. Okay, then we continue our walk. And now I come to a fork in the road. I have to decide, do I want to go up or down, or left or right? I think I will just go this way. Okay, so then now I get to a waterfall. Think of resistors as like waterfalls because there the voltage decreases. So I get minus, because I'm going down the waterfall and I'm going in the direction that the current is going, by the way. So I'm going down the waterfall. And so that's minus. Now, what's the voltage drop across this 5 ohm resistor going to be? Well, the voltage drop across a resistor is given by Ohm's law. The voltage drop across that resistor is the current through that resistor. So I5 is the current through that resistor. I don't know what I5 is, but it's the current through that resistor. That's what the name we gave it. Times R, which is 5. Okay. And then so then I'm down at the bottom of the waterfall. I'm over here now. And then I come back and let's see, I'm going to just keep going around the circuit on my walk. So far I'm just on a wire, which doesn't have any voltage changes. And then I'm back where I started. So my total change in height on my trip as a whole, it's got to be 0. We have 10 volts equals I5 times 5, or 10 volts or 10 volts over 5 ohms equals I5, which is equal to 2 amps. And that's what we got before. So I found I5. And now that I've found I5, I can use I total equals I5 plus I10. Or I total equals I5 plus I10. So now I have I total, which we found up there to be 3 amps when I do the math right. 3 amps equals, this is I total equals I5 plus I10 equals, okay, so 3 volts equals, 3 amps equals 2 amps plus I10, or I10 equals 1 amp. That is Kirchoff's rules.